Hello and welcome to Team VLSI. Today we are going to discuss setup and hold time equation in the series of STA concepts. So please like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can search Team VLSI on Google. So in previous session we have discussed all the possible scenario for the analysis. So we have discussed these 4 cases through which we will cover all these scenarios, and each case will have 2 sub cases. If you have not watched the previous session, you can go on the previous session through this I button. It will help you to understand this session. So in previous session we have discussed the case where launch and capture both elements are flip-flops, and specifically both elements are of same types, that is either both are positive edge triggered or both are negative edge triggered. Today we are going to discuss a case where launch flop and capture flop both are opposite edge triggered. For example, here launch flop is positive edge triggered and capture flop is negative edge triggered, and similarly launch flop could be negative edge triggered and capture flop could be positive edge triggered. So let's see the derivation for setup equation first. So here we have launch flop is positive edge triggered and capture flop is negative edge triggered. This dot symbol on the clock is clock pin is symbolize that this capture flop is our negative edge triggered flop. Okay, so at the clock pin we have the clock waveform like this, and our data will be launched by this launch flop once this positive edge moved from this clock pin to the CK pin of the launch flop, right? And in previous session we have seen that once this positive edge reached at the CK pin of the launch flop, after after clock to Q delay, data will be launched by this launch flop and captured by the capture flop on the next positive edge, right? But next positive edge, right? But here this flop is a negative edge triggered, so this will work on the negative edge of clock. So after launching the data, next edge will be this negative edge. So instead of capturing the data on this positive edge, it will be captured on this negative edge, right? So if this clock has clock period TCLK, then in this case we have only T/2 time to meet this setup time. So we have half clock cycle only on which our setup is being checked. So once clock is reached here, it will launch the data, and before T/2 time it should be captured by the flip-flop 2, right? So mathematically we can write it, theta should be less than T/2 instead of T, as we discussed in the previous session. So here it will be T/2. So theta should be less than T/2, where theta is our combinational delay plus this clock to Q delay, or we can write this equation like T clock to Q delay plus T combinational delay should be less than T/2. This is an ideal equation where latency and all the things is not covered. We will cover one by one everything. So now ideally both the edges should occur at this time of period, but in reality it doesn't. It takes some time to move this clock signal from this clock pin to CK pin of the launch flop. So suppose we have that time period is L1, then L1 is called latency of this launch flop, and similarly capture flop, suppose we have latency L2. So L for this clock edge will reach at this CK pin of launch flop after L1 time, and similarly this edge will reach at the CK pin of capture flop after L2 time. Okay, so let's include these two latency in our equation. So L1 plus TCQ plus T combo should be less than T by 2 plus L2. Now let's introduce one more practical scenario, that is setup uncertainty. So this edge will have some setup uncertainty of the occurrence, and what could be the worst case if this clock edge occur before the actual edge of occurrence. So we have to take care of this clock uncertainty. So we have to subtract the clock uncertainty time on the right hand side, right? So L1 plus TCQ plus T combo should be less than T by 2 plus L2 plus clock uncertainty TSU, right? Now let's introduce one more practical factor, that is the setup time of the flip flop. So what as per the definition of the setup time say that clock data should be reached on this capture flop before the setup time of the flop from the arrival of the clock edge. So again we have to subtract the setup time on the right hand side, right? Because we have to reach the data before the setup time, means at this point of time data should be reached at capture flop. So let's subtract that. So now our equation will be L1 plus T clock to Q plus combinational delay should be less than half of the clock period plus latency of the capture flop minus clock uncertainty minus setup time of the capture flop, right? So here you can see that this left hand side term should be lesser than the right hand side term in order to meet the setup timing, right? So left hand side part is the time, what it should be, it's the time taken to reach the data to D pin of the capture flop. So that is left hand part is called our data arrival time or AT, and right hand time is called data required time. So this term says that before this time your data should be reached at the capture flop, right? So we call it as a data required time or RAT, and we can see that this term should be greater in order to meet the setup. So our data required time is this much, right? And the difference of data required time and data arrival time is called slack. And you can see here if slack is positive, then only this term will be greater than this, right? So if slack is a negative, it means there is a set of violations. So let's simplify this equation a bit more. So we have seen this equation in the previous slide. So what we can do further, we can move this L1 to the right hand side, so it become L2 minus L1, and the difference, what is the L2 minus L1? It is the difference between the latency of capture flop and the latency of launch flop, and that is called our SQ between these two flops, right? So we can write this at the clock to Q delay plus combinational delay should be less than half of the clock period plus SQ between these two minus T setup clock uncertainty minus clock uncertainty time minus setup time. So this is our final setup equation, right? So what we have seen here, if launch flop see this waveform, capture flop will see a bit delayed waveform, that is the latency between skew between these two. Okay, and where our setup will be checked between this positive edge to the negative edge of flip-flop 2, right? In normal cases where both the flip-flops are on same edge triggered, our setup is generally checked between this positive edge to the next of positive edge. But in this case, where both the flops are opposite edge triggered, our setup will be checked between this positive edge to next negative edge. So we can say that in this case, our setup requirement is very tight. We have only half of clock cycle to meet the setup time. What will be the impact of hold timing? Okay, we will see in the next slide. Before that, here is one important information. If launch and capture flop are opposite edge triggered, then a half cycle will be there in between them. So such scenario is called half cycle path requirement, right? And I have a question here for my audience, that do we need to specify half cycle path as we do for multi-cycle path and false path in SDC? Do we need to specify half cycle path, or how will tool detect that? I would like to see your answer in the comment section. So next, derivation for the hold equation. So if this is the clock at the clock pin, then this clock will take certain time to move this launch flop. We have considered that L1 latency between the clock and arrival time at the launch flop. Okay, so on this positive edge, our launch flop will launch the data, and once data is launched by this launch flop, data will be moved and captured by on the capture flop, and capture flop will see the clock, a delayed version of original clock, right, from this clock pin. So if we have considered here that the difference between the timing of this edge is L2, that is the latency of the capture flop, right? So in case of setup, what we are making sure that this data should be reached before the arrival of next negative clock, that means this clock, right? But in hold, what we have to make sure that this clock path should not be fast enough that it will overwrite the data captured by the capture flop in the previous cycle. And where the previous cycle, in which edge data is captured in the previous cycle? Obvious, on this edge, right? So our data path should not be fast enough that it will reach before the proper capture of the data on the previous cycle. So we have to check the hold on this edge, right? Okay, so we have to check the hold on the previous negative edge, that means on this edge. So obvious, this is very relaxed for the hold check. So if theta is our combinational path delay and t hold is hold time of flip-flop 2, then mathematically we can write that t by 2 plus theta should be greater than t hold. Why t by 2 here? Because after t by 2 time, if we neglect this latency, so all the edge will come on this same time. So this positive edge will occur after t by 2 times, and it will take theta times to reach the data. So on the data arrival side, it will be t by 2 plus theta, and again we can divide the theta as a clock to Q delay plus combinational delay. So our t by 2 plus t clock to Q plus combinational delay should be greater than hold time of the flip flop 2, right? Now consider the latency. So we have clock this much of time, L1, that is the latency of launch flop, and L2 is the latency of capture flop. Then we can add these on both sides. So our equation will be t by 2 plus clock to Q delay plus combinational delay plus L1 should be greater than hold time plus L2, right? Let's consider one more scenario, that is hold uncertainty. And which way we have to consider the hold uncertainty? If this edge comes before, then we have no problem. But if this edge somehow deviates from its actual appearance and it will be late, then definitely we have a problematic scenario. So we have to consider its late appearance. We will consider this edge hold uncertainty, and suppose we have the hold uncertainty of THU, then we have to add this term on the right hand side, right? Now on the left hand part is the time taken to reach the data to this point, so it is called data arrival time, and right part is the required time to reach the data, so we generally call it data required time. And in hold analysis, opposite to the setup analysis, our data arrival time should be greater than the data required time. So data arrival time minus data required time is called here slack, opposite to the setup. In setup, we have data required time is greater than the data arrival time. For data required time minus data arrival time was the slack in setup case, but here it is opposite, right? So if this equation is if timing is meeting this equation, then definitely our slack will be positive, and if it is not meeting, then our slack will be negative. So a negative slack means hold time violations, right? Let's make this equation a bit more simplified in the next slide. So we have seen till here. Now the latency of capture flop minus latency of launch flop here. So and for this difference of latency is called skew, clock skew, right? So we can simplify that in this equation by taking L1 to the right hand side, and it will become L2 minus L1 here, and we can replace L2 minus L1 by T skew. So this is our final equation. Let's summarize this analysis. So we have a clock signal FF1CK like this, and next, and for capture flop we have a delayed signal, clock signal like this. So we have seen that our setup analysis is done between this positive edge to the next negative edge, between these two, right? So we have only t by 2 time to meet this setup, and we have seen our hold analysis is done one cycle before this negative edge, that means on this edge. So hold analysis we consider this negative edge, right? So here we have very tight condition for meeting the setup and very relaxed condition for meeting the hold. Here I have a very common questions. We every time heard that our hold time is independent of clock period, right? But you can see here in this equation our clock period is there, t by 2. So I have a question that may hold time depend on the clock period? What you think and what you analyze I would like to see your comment on the comment section. And in next session, it is going to be very interesting, because in next session we will discuss the case where latches are in combination of flip-flop. So in next case we will discuss one flip-flop and one latch is there, and that is very interesting case, because there is a concept of your time borrowing. We will discuss on that. So wait for the next session. So thank you for watching this session. If you find this video is relevant to you, please do like this video and subscribe our channel. Our channel is youtube.com/teamverify, or you can share these videos with your friends and colleagues. You can now reach us on our blog. We have started recently. You can read many good articles on our blog on www.teamverify.com, or you can follow us on the Facebook page. We have Facebook page, facebook.com/teamverify. Thank you. We will meet in the next session with very interesting analysis. Thank you so much.